So the first thing you might notice on this section is that it has two sections all combined into one. 5.4, 5.5, and they're titled the Fundamental Theorem. Anytime you see mathematics where they've got the word fundamental in it, it means that it's important. All right? Are you guys with me? All right, what did the word fundamental mean?
It's important.
It's important. That's good. I'm glad. Fundamental means important. Okay? So the first thing I'm going to give you is pieces of information that you might not have seen before if you haven't done a calculus course. The second half of this very front sheet, you're going to fill in for me on your own. So let me start with the stuff that is new, at least new for us right now. The fundamental theorem of calculus says the following. d dx, so the derivative with respect to x, of the definite integral from a to x of f of t dt equals f of x. In words, what this says is that the derivative of the integral equals the function itself. In other words, there is this relationship between them that is an inverse relationship. What's the inverse of multiplication? Division. That's an inverse relationship. The same type of relationship exists between finding this area under the curve and the slope of the curve, which are the two quantities that we've been finding this semester. So on an antiderivative, let f be a function. We call the function capital F the antiderivative of lowercase f if the derivative of capital F is equal to f of x. So in some sense, what we're about to do is to do everything we've been doing backwards. Yeah, it would probably be a very, very good idea for you to get the original gateway that's still on the table taken care of before you have to start thinking about both of these things at the same time.
Are we still taking it on Thursday?
You can still take it on Thursday. Thursday.
Gateway.
Oh, is it still on their schedule? We have to push it back because I didn't get through this section. It'll have to be pushed back till Tuesday. Thank you for asking.
Oh yeah, this is what the second gateway is going to be over?
Yes, this is the second gateway information. It's exactly right. Yeah. The second gateway needs to happen after 5455, and we're not finishing 5455 today. We're about half class period behind. That's okay. We'll get caught up. Have no fear. I will not leave you behind. Okay, does everybody have this written down? Because the next part is you remembering all the rules that you're supposed to know. And those of you who haven't finished the gateway, we'll see if you remember them now. This is half of them because I have two slides. It would not fit on one slide. These are the derivative rules. It tells you the page number they're on. Please don't flip to the page number. You should know these all. You should know them. Okay? So I'd like for you to take a minute to go down the list of everything that's on this page and this one. And I'd like for you to write the derivative rule that you know that we've done before. Okay, so I'll help you get started. First one, the constant rule. What is the derivative? Y equals b. What's the derivative of b? 0. So on the right-hand side for the derivative, you're going to write down y prime equals 0. Okay, so I'd like you to fill in the right-hand side with all the derivatives that you know. If there's something that you can't remember off the top of your head, that's okay. Don't fill it in, or use pencil and erase it in a minute or something if you need to. We'll make sure everybody remembers all those pieces. And then we're about to flip the script. Okay, linear function rule. What is the derivative of ax plus b? It's a. Power rule. What is the derivative of x to the n? No, you're thinking of the b to the x rule. The other one, yeah. N x to the n minus 1. Yeah, so if the base is the variable and the number is the exponent, we're going to bring the number down and so forth. The next one's the one that you were thinking of, Lainey. So what is the derivative of b to the x? Right, bx ln b, though. It's always the natural log of the number, not the variable. Bx ln b. Okay, the two at the bottom are the exponentials with e in them. So what's the derivative of e to the x? E to the x. The second one, I know it's not one that we sort of set up as its own rule, but it does come up frequently, and it's a chain rule application. What's the derivative of e to the ax? E to the ax, and then times a. If you want to write the a in front, be my guest, but it's going to be written down there somewhere. It's multiplied by the exponents, variables, coefficient. Okay, second slide. What is the derivative of the natural log of x? 1 over x. And what is the constant multiplier rule? What happens when you have a number times f of x and you take the derivative? Keep the number, and then you do the derivative of f of x. Good. And what happens when you've got a sum or a difference? Yeah, you just take their derivatives individually and add or subtract them from one another. Okay. So those are all of the rules that we've done so far. That's it. The simple rules. I don't mean product rule and chain rule and stuff like that, but those are the simple rules that we did. So what we're going to do next is we're going to take mostly the same rules and we're going to go backwards. So as we do that, you'll notice some of the names are the same. There's a couple of small changes in the names as well. Couple of changes in the functions themselves. This shouldn't say derivative. Obviously, I cut and paste did not get the anti on there. These are the antiderivatives, which is what your paper says. And we're going to write down the antiderivative for each of these functions. So as we do this, what you have to think to yourself is, how did I get this derivative? Because what I have is now a derivative. All right, so the first one, y equals k. Close. Kx. And we use capital letters when we find antiderivatives. So this is like capital Y equals. But there's one other thing we have to do. Close. It's not dx.
Plus x.
You're so close. Somebody said it. Plus a constant. We usually call it plus c at the end. Okay, so let me talk to you about what I just did. The part that I just wrote down, if you took its derivative, kx plus c, what is the derivative of kx plus c? K, which is where we started, right? I mean, that's what it started out as. Every time you do an antiderivative, you're going to put plus c on the end of it. Because it always could have one constant on the end, because when you take the derivative of a constant, what happens? It goes away. So there's always the possibility of having this plus c on the end. Because of that, we actually call this a general antiderivative. Graphically, when you add something to the end of a function, all it does is it shifts it up and down. So no matter what the shape of the function is, the shape stays the same, it's just shifted, all right, with plus c on the end. So that makes sense because derivatives actually calculate slope. They don't care how far up and down you are actually on the graph, all right? So let's keep going. The next one is the simple power rule. So with the power rule, what we did before is we took the current exponent and we brought it down in front as a multiplication factor, right? So what is the opposite of making something multiplied? Divided. So you're about to see me do something with division on this problem. The next thing was that we took the exponent and we decreased it by 1. What would be the opposite of that? We increase it by 1. So those are the two features that you're going to see happening on this function. We're going to increase it by 1 first. So this is x to the n plus 1. And then we're going to divide by the new power. And we're going to put a plus c on the end. Okay, so now imagine taking the derivative of that. If you took the derivative, you'd take the n plus 1 down in front, and you decrease it by 1 to n, and then the n plus 1 in the front and the n plus 1 on the bottom would cancel out, right? So if I took the derivative of what I just wrote down, I would get back x to the n. All right, this is the natural log rule. This one's kind of a funny looking one. You'll notice that this says y equals 1 over x. Well, when we did derivatives, we wrote that as x to the negative 1, and we used the power rule, and it was no big deal. But we're going backwards. Whose derivative was 1 over x? ln x was. It was the log function. So this is actually ln x with one caveat. Over here, we have a plus c, that's true. I've got one more thing to deal with on this one. Over here, take a look at the log function. Do you see the condition that had to be true for the log function to work? X had to be positive. And in fact, some of you ran into some problems on a homework problem where you came in to me and you were like, it's not letting me work with something. I said, well, of course it's not, because you're trying to put negatives inside of a log. It's giving you an error because of that. So that's what's going to happen here, and the only way that we can do that to make something positive is we put in absolute values. Okay, that forces it to be positive. It can't force it to not be 0, but at least it forces it to be positive versus negative. Okay, b to the x rule. So what was the derivative of b to the x? Right, b to the x times the natural log of b. So what's the opposite of times? Division. So this one's going to be b to the x divided by the natural log of b plus c. All right, e to the x is about to become your second best friend. It was your first best friend before, and now it's your best friend the second time. That's what that means. If the derivative of e to the x is e to the x, what do you think the antiderivative is? Yeah, e to the x and then plus your c. You got it. It's fantastic. All right. Say again. What one? Oh, prime notation had to do with derivatives. These are antiderivatives. So the notation for doing an antiderivative is that we take a lowercase letter and we make it capital. That's the notation that's used. Yeah. All right. How about this one? We didn't have this actually as a real rule before, but we kind of created it as such because we can use it for some other features. When we had e to the ax, what was the derivative of e to the ax? E to the ax times a. So what would be the opposite of that? Divided by a. So this is e to the ax divided by a and plus c. Two more rules at the bottom, and they are very straightforward ones as well. What happened when we did a constant times a function and we took its derivative? We multiplied the constant times the derivative, right? It works exactly the same if we're doing antiderivatives. If we have a constant, we multiply that constant times the antiderivative. And the antiderivative is capital F of x. And still we have a plus c. And if we have a sum or a difference, and we took the derivatives, we just took the individual derivatives and we put the plus or minus between them, right? And we do the exact same thing when we do the antiderivatives. We take the individual antiderivatives, which is capital F of x, whoops, and a capital G of x notation, and we put a plus c at the end of it. Okay, we're going to do an example before we leave, because I can tell you all these rules and then you're going to immediately walk out the door and forget them if we don't do at least something to practice it. So this is our attempt at the something to practice it. And we'll finish more next time. Let's see if we can do a couple of these, maybe the first three. We'll see. Okay. First one, 7x to the 2. That's the first part, right? So the x to the second will do what? You add 1 to the 2. So that's x cubed, right? What else will we have to do? divide the 3, and the 7 is a constant multiplier, which means he just comes along for the ride. Write it in front, write it with the x cubed, doesn't matter. It's 7x cubed over 3. And then what is the antiderivative of e to the x? E to the x. And you need a plus c. When you do the gateway for this, which we're going to do next Tuesday, so we'll put it for a week from now, and that's what you should be starting practicing. I would hope you can get your derivative one done sooner than starting practicing this, but the gateway for this one. Please remember your plus c's. I had a student who would have gotten bonus points on a test. He actually had all 20 questions right, but he didn't put a plus c on any problem at all. It was so sad. Yeah, so don't make that you. We don't want that to happen to you. Okay, this next one is a little more interesting. It's got a little more going on, 3 pieces for one part, but it has 1 over 3x. Now, some of you were doing some derivative stuff where you had a 1 over 3x on the last homework assignment, actually. And you can treat this in a number of ways. But the easiest way to treat it for the purposes of antiderivative is remembering that this is 1 over 3 times 1 over x. That's what 1 over 3x means, okay? It really does. So the 1/3 is a constant multiplier, which means the antiderivative will simply have a 1/3 in it. What's the antiderivative of 1 over x? That is ln of the absolute value of x. And that's another common feature that we tend to forget, right? This is the rule right here. Got to have a positive input. 1/3 and natural log x. How about the e to the 3x? E to the 3x and then divided by 3, right? What's wrong? Oh, my screen's not showing up for you. Okay, how about the plus 2 at the end? What's the antiderivative of plus 2? Yeah, you get 2x. So you reattach the x that would have removed itself when you took the derivative of 2x. And then I need a
C.
plus c. Let's do the last one in this set and we'll stop. All right, this is the most fun one here because it's got so many cool parts to it. Aren't you excited? Okay, where'd my paper go? All right, 9 to the x. What's the antiderivative of 9 to the x? Notice all the 9s in it. Isn't that beautiful? Good. That's the b to the x rule. That's 9 to the x divided by natural log 9. When we do derivatives, it's times natural log 9. So when we do antiderivatives, it's divided by. All right, the 1/9 x. What's that going to become? What do I do with the 1/9? Keep it. I don't do anything really with it. It's just there. What do I do with x? I do x squared over 2. That's right. You increase the power by 1 and divide by the new power. This is tripping some of you guys up, this notation. How else can I write 9 squared x? 9x to the 1/2. Okay, so thinking about that, what do I do with the 9? Leave it. What do I do with x to the 1/2? I increase the power by 1. So 1/2 plus 1 is actually 3/2. And then what? I divide by 3/2, or you could multiply by 2/3 if you want to multiply by 2/3.
You also have to divide them.
Divide by what?
9.
Nope, it's a constant multiplier. Oh, we missed one thing. Plus C. There you go.